Okay, so this chapter 4, involves fossil fuels. We have seen that different fuels are characterized by different heat of combustion, and it's a source of energy that is used in several applications in the energy and science, in the science and technology field. So we have already seen that fossil fuels can be used to drive power plants. Another application also that is widely used is in the automobile sector. So we have fossil fuels that can drive cars. And as you know, currently we are working on hybrid cars that are rely both on electrical and fossil fuel energy. Uh, so we need to understand how to quantify, if you want, the energy emitted from combustion of fossil fuels, and how we can try to assess the emissions of CO2. Yani to control CO2 emissions, we need to know how to write the chemical equations, how to determine for each mass of fuel burnt what will be the level of CO2 emissions, to know what strategies can be developed in order to capture this CO2 and store it if possible. Okay, so we'll do several problems in order to understand how to deal with these ideas. In the first problem, we'll consider any hydrocarbon in general. So just 1 minute. So if you take any hydrocarbon in general, it's composed of two main elements, which are the carbon, C, and H. Okay. So we can define, if you want, a hydrocarbon by the percentages of carbon and H it contains. Now, these percentages sometimes can be given in, if you want, in percentage of mass, sometimes in percentage of volume. And all we have to do, and we need to know how to convert from one to the other, as we'll develop together in problems. So first, in this first problem, we consider that we have a hydrocarbon fuel that is composed of atoms C and H. And we know the mass percentages of carbon and hydrogen in this fuel. And the question is to determine first what is the quantity of air required for complete stoichiometric combustion. And we will evaluate it in kilomole per kilogram. Then we'll evaluate it in kilogram of air per kilogram of fuel. So first, to be able to answer this question, we need to know what are the main reactions that will take place. We already have seen together in chapter 4 that for complete combustion, we have first carbon plus O2 will give us CO2. And our purpose is to know what is the amount of CO2 produced in order to see what are the technologies that should be developed to capture it and store it. Okay, so C plus O2 equals CO2. And the second reaction is for hydrogen. So H2 plus, so here to determine the coefficients, we know that the product is H2O. And you know that in order to find the coefficients, we rely on conservation of mass. So for each element, the number of elements from the left side should be equal to the number of elements from the right side. So already you have two atoms of H here and two atoms of H here. So we are fine with hydrogen. Now for oxygen, we have one element here and two elements here. So we should multiply here by 1/2. Okay, so from these relations, we can determine that the quantity of O2 required in total, okay, will be equal to know what is this quantity. We say the quantity of O2 should be able to completely burn carbon and H2 in a stoichiometric way. So we know from this equation, from the first equation, we can write the following. We can say that 1 kilomole of carbon will need 1 kilomole of O2, okay, to produce 1 kilomole of CO2. So 1 kilomole of C will require 1 kilomole of O2. But in this problem, we have percentages and mass. So to be able to do the analysis here, we say if we have a mass percentage of C, this means that if I have 1 kilogram of fuel, in 1 kilogram of fuel, I will have C kilogram of carbon and H kilogram of hydrogen. So 1 kilogram of fuel will contain C kilogram of carbon and H kilogram of H. H or H2 is the same because when I talk about the mass of H or molecule H2 will be the same at the end. What will vary is the number of kilomoles, okay? So I have H kilogram of H or H kilogram of H2, it's the same thing. Now, since they asked me to do the analysis per kilogram of fuel, so in this 1 kilogram of fuel, I have C kilogram of C and H kilogram of H2. And we know that the molar mass of carbon is 12. So the molar mass of C is 12 kilogram per kilomole, okay? So we can say, if you want, it's a proportional relation. 1 kilomole contains 12 kilogram. So if I have, in case I have C kilogram, this will correspond to C over 12 kilomole of carbon. So I have C over 12 kilomole of carbon in my fuel. And we have seen from the reaction that the number of kilomole of C will be equal to the number of kilomole of O2. So if I have C over 12 kilomole of carbon, it will need C over 12 kilomole of O2. So to burn completely carbon in a stoichiometric way with complete combustion, when we say complete combustion, and we have formation of CO2, we don't have formation of CO, okay? So we have C over 12 kilomole of O2. So this is until now the quantity of oxygen that is required to burn the carbon mass present in my fuel. But as we have seen, we don't need only to have to burn carbon, but also we need to burn completely hydrogen present in the fuel. So this is the first quantity required. We should add to it the quantity of oxygen that is required to burn H. So now we go to the second relation. The second chemical relation is H2 plus half O2. That will give me H2O. So we can say here that 1 kilomole of H2 will need 0.5 kilomole of O2 to do complete combustion. And now we have seen together that in this fuel we have H kilogram. So we have here H kilogram of H2. And we know that the molar mass of H2 is 2. Okay? So if we have H kilogram of H2, this will correspond to H over 2 kilomole. Okay? So we have H over 2 kilomole of H2 in our fuel. And since the number of kilomole of O2 is half the quantity, is half the number of kilomole of H2, so each H over 2 kilomole of H2 will require H over 4 kilomole of O2. So we can deduce that if C and H represent the percentages in mass of carbon and hydrogen in a hydrocarbon fuel, then the quantity, the total number of O2 in kilomole will be equal to C over 12, which is the quantity in kilomole needed to burn carbon. And we should add to it H over 4, which is the quantity of O2 needed to do a reaction with H2. Now, in this problem, they want us to calculate the quantity of air required in kilomole of air per kilogram of fuel, okay? So to be able to determine the quantity of kilomole of air per kilogram of fuel, we need to know what is the percentage of O2 in air. Okay, we know that for O2, we can talk about percentage in volume and we can talk about percentage in mass. Okay, so first, if you are interested to find L0, which is defined as number of kilomole of air per kilogram of fuel, so you need to quantify air in kilomole. Okay, and we know that kilomole is proportional to volume because each kilomole of any, if you want, of a certain gas is equivalent to 22.4 meter cube. Okay, so we have a proportionality between 22.4 meter cube. We have a proportionality between number of kilomoles and volume. Okay, that's why if we need to determine the quantity of air per kilogram of fuel, we need to know the percentage in volume of O2 inside air. Okay, so here already we did the analysis per kilogram of fuel. So, and we have seen that the quantity of O2 required is NO2 equals to C over 12 plus H over 4. But O2 constitute 21% in volume of air. Okay, so we can say that this is equal to the number of kilomole of air times 0.21. Since NO2 represent only 21% of volume of air, so this is equal to 0.21 times the number of kilomoles of air required. Okay, so then we can deduce that to find what is the number of kilomole of air that we named L0, so number of kilomole of air requires is L0, is equal to 1 over 0.21 times C over 12 plus H over 4. So this analysis, okay, whatever is the type of hydrocarbon, once you determine the percentage in mass of carbon in it and the percentage of hydrogen in it, you can calculate the quantity of air in kilomole per kilogram required for complete stoichiometric combustion. Now, of course, if you supply a larger quantity of air, okay, you will have excess of air. And if you supply a quantity of air that is lower than the quantity required, you will have incomplete combustion. And we try to avoid this because incomplete combustion will lead to formation of monoxide of carbon, CO, not only CO2. And CO is much more harmful than CO2. So we try to avoid having incomplete combustion. This is why we should determine the stoichiometric quantity and try to supply more to avoid any formation of CO. Okay, any question on this problem? Okay. Now, they also asked to determine the mass of air in kilograms that is required. Okay, so here we have to approach. we can say once we know the number of kilomole, we just need to know the molar mass of air, okay? Because we know that the molar mass will relate the number of kilomole to the mass. So if we know the molar mass of air, we can say that molar mass of air is equal to the mass of air required, which is L0, I named it L0, over the number of kilomoles, which is L0. So we can deduce that if we want to determine the quantity in kilogram of air per kilogram of fuel, we just have to multiply the number of kilomoles by the molar mass of air. The molar mass of air is around, it's very close to 29, okay? So it's around 29 or 28.9. Okay, so now another approach to find L0 will be to use from the beginning the analysis in kilograms. Yani we said, for example, that if we have C kilogram of carbon, okay? So we have seen that C kilogram of carbon will require C over 12 kilogram of O2, okay? And sorry, C over 12 kilomole of O2. And once we know the number of kilomole of O2, we can deduce the mass of O2 required. So the mass of O2 required here will be MO2. We just have to multiply the number of kilomole by the molar mass of O2. We know that the molar mass of O2 is 2 times 16, which is 32, okay? So we can say that the mass of O2 required in this case will be 32 times C over 12. So the quantity in kilogram of O2 required for combustion of C kilogram of carbon is 8 over 3C. Okay. Now, we also can evaluate the mass of oxygen required for combustion of H kilogram of H2. So we said that if we have H over 2 kilomole, which correspond to H kilogram of H2, okay, we'll need H over 4 kilomole of O2. So to know the mass of O2 required, we just multiply by the molar mass of O2, which is 32. So we need then 8H kilogram of O2 in order to do the reaction with hydrogen. So what is the total mass of O2 required? We can say that mass of O2 required for stoichiometric combustion is equal to the one needed with carbon, which is equal to 8C over 3, plus the mass required to do reaction with hydrogen, which is plus 8H. Okay, and now if you did the analysis in mass of O2 required, we know that O2 constitute 23% of percentage in mass of air. So we can deduce that the mass of air required per kilogram of fuel, which is L0, is equal to 1 over 0.23. And you can verify that the two methods will give you exactly the same result. okay? So 1 over 0.23 times 8C over 3 plus 8H, okay? Any question on this? So now this general analysis can be used in other problems with numerical values, okay, to directly find what is the quantity of air required for complete stoichiometric combustion. Let us take another problem to see how to deal with such percentages. Okay. So consider in problem 2, we'll consider a fuel that is a mixture of several hydrocarbons. So a fuel is constituted by 80% in mass of C3H8 and 20% in mass of C2H6. We want first to calculate the quantity of air required for stoichiometric combustion of fuel. Here you have several approaches, okay? You can use the result that we have derived together in previous problem. We'll do it together. But also, if you don't know this method or you didn't perform this calculation before, you can simply write the chemical equation, okay? So you can say that I have a mixture of C3H8 and C2H6, okay? And this mixture, let's say, will contain a certain percentage in volume of C3H8 and a percentage in volume of C2H6. Please pay attention for percentages. And if you have the percentage in mass, you can deduce the percentage in volume, but they are not equal, okay? And we should know where to use the percentages and where to use the percentages in volume. And for example, in general, if you want to write a chemical reaction, we need to know the number of kilomoles of the reactives. We can say, for example, let us consider that we have a kilomole of C3H8. Okay, and B kilomole of C2H6, okay? If I know the number of kilomoles involved, I can deduce the percentage in volume because we said number of kilomole is proportional to volume, okay? So if I know the number of kilomole of C3H8 and the number of kilomole of C2H6, I can say that the percentage in volume of, let's say, C3H8 will be equal to A over the number of kilomole of C3H8 over the total number of kilomole, which is A plus B. And in this way, I find the percentage in volume of C3H8. And I can deduce that because I just have two fuels here, two chemical components mixed together, I can deduce that for C2H6, the percentage is 100 minus the percentage of C3H8, okay? Or I can calculate it as B over A plus B. So whenever you have the number of kilomoles of each of your constituents or reactives, you can deduce the percentage in volume. And you can do this easily here because you have the percentage in mass. When they give you the percentage in mass, this means what? This means that if I have 80% in mass of C3H8, if I have 1 kilogram of fuel, I can do the analysis. If they didn't give me what is the mass, I can do the analysis per unit mass. So I consider 1 kilogram of mixture, okay? In this 1 kilogram of mixture, I will have 80% of C3H8. So it's equal, I will have 0.8 kilogram of C3H8. And I will have 0.2 kilogram of C2H6. Okay. And now all I have to do is to determine the corresponding number of kilomole. And we know that in order to find the number of kilomole, so we called it A for C3H8, okay? To get A for C3H8, number of kilomole present in 1 kilogram of mixture, I should consider the mass present over the molar mass of C3H8. Okay. So we know that for C3H8, we have 0.8 kilogram. So it's equal to 0.8 over the molar mass is simple to determine because I know that for carbon, the molar mass is 12. And for hydrogen, the molar mass is 1. So I just have to multiply, to do 3 times 12 plus 8. So this will give me the number of kilomole of C3H8 present in 1 kilogram of my fuel. Now to determine B, it's a similar equation. I take the mass of C2H6 that is present, which is 0.2. And I divide it by the molar mass of C3H8, C2H6, which is 2 times 12 plus 6. Okay? And now, once I have A and B, I can deduce the percentages in volume of C3H8 and C2H6. Okay? Why I need these percentages? Because when I want to write my equation, okay, I need to know, let's say for one, if I have 1 kilomole of mixture, when I get the percentages in volumes, I can determine in 1 kilomole, the percentage in volume I obtained for C3H8, let us call it C. Then I can say in 1 kilomole of mixture, I will have C kilomole of C3H8 and D kilomole of C2H6. And now I can determine then, if you want, the number of kilomole of O2 required for the combustion of this mixture. So I can write C kilomole of C3H8 plus D molecules or D kilomoles of C2H6 will require how many kilomole of O2? So I should determine what is the number N of kilomole of O2 required. So N is unknown. To obtain, we know that what are the products of such combustion? CO2 and H2O. So CO2 plus H2O. Here, okay, I need to put coefficients for CO2 and H2O. It's very simple. I just rely on conservation of mass. So I can say how many atoms of carbon I have in reactives. I have 3C. So in number, since I C represents the number of kilomole, C kilomole of C3H8 will contain 3C kilomole of carbon. And D kilomole of C2H6 will contain 2D kilomole of carbon. Okay, so I should have in the products also the same number of kilomoles. So I can say that I should have here the coefficient of CO2 will be C3 plus 2D. Okay, so this is the coefficient to use here. This coefficient is 3C plus 2D. Now for H, okay? Similarly, I do the same approach. Concerning the number of kilomoles of H in the reactives, I have 8C plus 6 times D atoms of H, okay? But since here I have H2, not H, okay? So if I have 8C plus 6D kilomole of H, I will have 8C plus 6D over 2 kilomole of H2 because each 2 atoms of H will form 1 molecule of H2, okay? So now I determined the coefficient of CO2 and I determined the coefficient of H2O. Once I do this, next step will be to find my unknown N. And also here's the same concept. I have the number of kilomole of O from this side, from the reactive side, is equal to the number of kilomole of O from the product side. So from the product side, I can say that the number of kilomole of O2 is equal to the following. So I can say that I have for O now, when I do the conservation of mass for O, I can say that from this side I have 2N. 2N kilomole of oxygen is equal to, from this side I have 2 times the coefficient of CO2, which is 3C plus 2D. Plus, for H2O, I have to take the coefficient times 1, okay? So plus 8C, which is over 2, yani plus 4C plus 3D. Okay, so now N will be equal, if I divide by 2, both sides, I can find N function of coefficients C and D. Okay, so this is a first approach to determine what is the number of kilomole of O2 required for the combustion, okay, of 1 kilogram, if you want, of 1 kilomole of my mixture. But keep in mind, okay, if you want to do the analysis per kilogram, yani in general, I will specify for you, or do the analysis per kilomole of your fuel or per kilogram. If the analysis is per kilomole, we are done. If the analysis is per kilogram, what will only change, if you want, is the coefficients. Yani here, we have determined together that for 1 kilogram, we have A molecule of C3H8 and B molecule of C2H6. So if you want to do the analysis per kilogram of fuel, you will use the number of kilomole A of C3H8 present in 1 kilogram of fuel. Okay, so this is the only difference. And you replace C and D by A and B, and you will be able to find the number of kilomole of O2 per kilogram of fuel. Now, once we find the number of kilomole of O2, in order to deduce the number of kilomole of air required, we just have to divide by 0.21. Okay, so this is the first method that just rely on writing the chemical equation, including the constitution of the fuel, and getting the coefficient of O2. Second method, which is much easier, is to use the result of a previous problem. In the previous problem, we said that the number of kilomole of air required per kilogram of fuel, and we named it L0. Okay, we considered that L0, which is the number of kilomole of air per kilogram of fuel, can be just determined from knowing the percentages in mass. So by doing just C over 12 plus H over 4 and this is the quantity number of kilomole of O2, we divide it by 0.21. So you can directly apply this result here. All you have to do then is to determine the percentage in mass of carbon and the percentage of mass of H in your fuel. How to do this? We go back to the percentages they gave us. So they said in this problem that we have 80% of C3H8 and 20% in mass of C2H6. So the only problem will be how to calculate percentage of C in mass and percentage of H in mass. Okay, it's really simple. We just have to use the given. So we say, since we are doing the analysis per kilogram, we say that 1 kilogram of fuel will contain 0.8